Hello, I am the project manager for the UCI solar airplane project. Uh, so in this video, you'll find more information about our spring 2021. I'll be making a little introduction about what the main purpose of the project is. And then the 4 sub-teams will be explaining what they've achieved this quarter in the midst of the pandemic. The main purpose of this project is to create an unmanned air vehicle that would help in natural disaster relief efforts, giving an edge over the situation to humans so that they can analyze the situation better. With a camera that will be able to transmit images to a human and a GPS to be able to recognize the specific area at which the camera is giving the images of.
Hello, my name is Preston Sterling, and I'm the avionics sub-team lead for the solar airplane project. During spring quarter, we did not have access to the lab and thus were unable to manufacture. However, all the parts necessary have been ordered and are with us. These parts include all the solar cells necessary for the aircraft, equipment for manufacturing lithium-ion batteries, and charge controllers. So this quarter, we were able to verify that the planned flight controller, the Pixhawk system, works, except for the GPS unit. We were also able to test individual solar cells under indoor lighting conditions and verified their specifications against the provided power curves. Lastly, we worked on a payload drop mechanism with a spring-loaded door that opens when a servo motor lock is disengaged, dropping its contents below. For example, this would be particularly useful if someone on the ground required a package to be dropped. Once again, we have all our documents detailing how we would build and test the actual solar system, involving testing and assembling batteries and the cell array, and we will be sure to pass this information along to the 2021-22 team so that they can manufacture the aircraft successfully.
Hi, my name is Alexander Toby, and I am the fuselage lead of UCI Solar Airplane, and I'm going to be talking a little bit about some of our spring updates and what we did this quarter. To begin with, unfortunately, our original plan of fabrication in the lab was obviously canceled due to lab availability and the COVID situation. So instead of taking our previous design and expanding it into the lab, we were actually able to further optimize it and look at what kind of constraints and what kind of issues did we have before, work around that, and ultimately create a fuselage that is more optimized, has more functionality, and is more lightweight. And I'm going to be talking a little bit about that. To begin with, the first thing that we optimized and one of the constraints that we had previously was the way in which the wing box was actually placed inside of the fuselage. To begin with, previously our payload mechanism was actually going to be mounted in between the wing box, but this posed potential issues because due to the dimensions of the internals, it kind of limited the way in which we could have the size of the payload. So if we wanted to have a larger payload, this would have been potential issues. So as a result, we tried to fix this by making the wing box a top mounted wing box and then shifting all the components up. And we needed to obviously prioritize structural integrity and making sure that this shift wasn't going to compromise the previous structural integrity. As a result, we looked at ways in which we could, create additional pieces, such as this white piece as shown in the bottom left here, which is actually going to be a 3D printed mounting piece that'll connect the bulkhead to the wing box itself and create ultimately the sandwich layout in which long runs will be running on the top, as well as additional spars on the side, and make sure that it's completely locked in. We use stress tests to confirm our findings to make sure that it was good to go. But ultimately, we made changes to the wing box in which we were able to, again, add this functionality of having the payload now be below the wing box so that it can more. Furthermore, we also had inclusion of the tail push rods, which will allow us to use servos to control the rudder and elevator deflection, depending on whether or not we want to increase angle attack, yaw pitch, and those kind of parameters. So a lot of these inclusions we didn't have in last quarter, and due to availability, we're actually able to kind of focus on that, perform stress tests, and ultimately redesign our wing box to better fit our needs.
Hello, my name is Gabriel Nicholas, and I am the sub-team lead for the tail sub-team here on the UC Irvine Solar Airplane project. So for some spring updates, there weren't too many modifications made to the plane other than the tail fuselage connection itself. And that connection is that little white part you see at the beginning of the tail. That is what connects, like as the name implies, the tail to the fuselage. We were able to do some weight reductions to that. And apart from that, we also designed a jig that would allow for perfect spacing between the airfoil ribs when we were putting the tail itself together. Now, that 3D connection point itself, it was reduced to about a 25% infill and is going to be printed out of ABS. Now, unfortunately, we did not get lab access for this quarter, which was actually kind of needed if we were going to obviously build the plane itself. But we were able to reduce it by about 2 ounces, making the entire thing about 1.5 ounces. And it was going to be printed out of ABS, and we would need access to a 3D printer over at UCI because those have enclosures, because ABS is kind of harmful, the toxins and fumes that come out of that when it's being printed, and also because of the build volume of that connection point itself. But that's really it for tail during the spring quarter.
And hello, my name is Jeremy. I'm the wing sub-team lead for the spring quarter. So this quarter, we optimized the wing for manufacturability. Unfortunately, we were not able to make it into the lab, but we did change several different aspects of the wing due to constraints of their ability to be made by a UCI student. So the first thing was the leading edge member. You'll see it here in the first slide. So this wing tank, as we called it, was unfortunately not able to be manufactured with what we were capable of using. So we did end up changing that to a carbon fiber spar instead, which did actually give us less wing deflection during flight. So that turned out to be good. Additionally, we changed our box spar design. So initially the box spar was also meant to be one long piece. So that was not going to be able to be laser cut. So we changed it into several different segments, and to keep the rigidity of the spar, we added wood blocks where these segments met, and we'll be screwing those in. Additionally, for the construction of the wing, we designed a jig to hold the ribs in place while the wing was assembled. And finally, to do better finite element analysis of the wing's components to decide which pieces of wood we should specifically use for the spar and which should be used for the ribs. We designed a test to determine the Young's modulus of each piece. So using strain gauges and a Wheatstone bridge and the LabVIEW software, we planned on clamping each piece to the table and determining what the Young's modulus was, since the vendor that we used to purchase the balsa wood did not give us the material properties for any of the pieces to allow us to make accurate analysis of the wood without having to guess on the grain. And that's it for the wings team. Thank you very much.
So that was a presentation for spring 2021. I hope you enjoyed it. If you have any questions or you would like to know more, please reach out to this email, as I will be responding through summer. And if anything, I will connect you with the next project manager. Thank you very much for your time, and I hope you have a great day.